This is chapter 3 for industrial networking. It is the EIA-232 interface system. This is by me, Avery Dvorak, and my partner, Peter Marinelli.
The learning objectives today is how to fix the following problems: incorrect EIA-232 cabling, male/female D-type connector confusion, the wrong DTE/DCE configuration, handshaking, incorrect signaling voltages, excessive electrical noise, and isolation. So this was developed for interfacing DTE and DCE. The DTE is data terminal equipment, so like a computer or a printer. DCE is data circuit terminating equipment, so a modem. DCE receives data from the DTE, and you can see a little picture there.
All right, so here are the major elements of the EIA-232 system. There are electrical signal characteristics, which includes the input and output voltage. They have to be the same or else you will get glitches within the system. It also includes as you can see in the picture there is the driver, which is the transmitting end of the EIA-232. And then you also have the receiver, which is obviously the receiving end. The driver is used to adjust the voltage to the correct level to be sent out, and the receiver translates the voltage to the correct level so that it can interface with the microprocessor. There's also the mechanical characteristics, which is the cord itself, which plugs into the socket. Most common EIA-232 equipment uses either a DB9 or a DB25 connector, which is basically just the number of pins on the port or the connector itself. So here is the functional description of interchange circuits. Basically, these are just some common descriptions that you'll see when looking at certain EIA-232 connections. So it's just like a basic little descriptor. So for example, some of the most common ones are transmitted data, which is TXD. That just means data that's from the DTE, or RXD, which is the received data that's coming from the DCE. RTS is request to send. That's obviously the DTE or the sender. It's requesting to send the data. And then CTS is the callback from the DCE informing the DTE that the data is okay to send.
So steps of operation. So the first step, user dials number of remote computer. 2, when received, the ring indicator pulses on/off, then sends a request to send the line to send line on. Receiving modem answers it and then transmits a signal and asserts the DCE ready line. Initiating modem asserts the data carrier to detect DCD line, and initiating terminal asserts its DTR. Then the modem responds by asserting its DTE ready line. The receiving modem asserts it's clear to send the CTS line, which allows the data to transfer from the remote computer to the initiating side. Data is transferred from the receiving DTE to the receiving modem. The receiving computer then transmits a short message to indicate that it can proceed with the data transfer. The original modem transmits the data to the original terminal. The receiving terminal sets its request to send line to off. The receiving modem sets the CTS line to off, and then the receiving modem switches its carrier signal to off. The original terminal detects that the DCD signal is off on the original modem and switches its RTS line to on. The original modem then knows that the transmission can continue by setting the CTS line to on. Transmission of data continues from the original terminal to the computer. When complete, both carriers are switched off and the DTR is set off. The full duplex requires transmission and reception to occur simultaneously.
All right, so here's a summary of the different revisions of the EIA-232 standard interface. So the first one is the revision C. This one was limited to a 15-volt maximum across both lines and a 50-foot distance between the receiver and the transmitter. But with revision D, they increased it up to a 25-volt limit maximum. And in place of a distance constraint, they had a maximum capacitance limit of 2,500 picofarads. That's pico, right? Right, Peter? Back me up.
Yes, Pico, you got it.
Picofarads. Okay. So then with the revision E, that's when they upgraded from the 9-pin connector to the 26-pin connector, which allows them for more pins and allows them to interface with more standard and modern systems. So next is the limitations. The first one is point-to-point limitations, which limits the use of smart instruments, which is more so a problem today because this standard is fairly old. So most of the problems come up when trying to translate it into modern applications. The next one being the 50 feet distance limitation that I just talked about. This is a problem when you're trying to connect multiple instruments to each other. The 20 kilobyte per second rate is another limitation, being too slow for most applications, and as well as the signal levels, like I talked about, not being compatible with most standard power supplies.
So the troubleshooting introduction, important factors to consider during installation is one device a DTE or is it a DCE? So traditionally, a DTE is a male and DCE are female. You also check for one male and one female port of the same size. Understand the speed of the communication. Understand the distance between equipment. Check the noise in the environment and check that the software is set up correctly.
So here's your typical approach to troubleshooting one of these systems. So the book provided this handy flow chart you have here. So first off, you want to find out if it is a DTE or if it is a DCE. So first you're going to test the TXD, which is the second pin, and you're going to see if there's a negative voltage across that pin. And if yes, then you know it's a DTE, but if not, you're going to do the same thing across pin 3. If that gives you a negative voltage, you're going to do, well, you'll know that it's a DCE. And if not, then, you're out of luck and you got to try some more of these in-depth troubleshooting techniques, such as trying to eliminate hardware handshaking, checking the protocol used for the DCE and DTE devices, or checking the application software if software handshaking is used. So here's multiple test equipment that they use to test these systems. We have the three most important ones here. The first one is the breakout box, in which you see a little diagram of it there on the right. You can see the different test points on it. You can use that to use a multimeter at the test points to detect the continuity for each line. Next up is the null modem. This is used when testing two devices of the same gender. So you can see over here on the right, this is testing a DTE for a DTE. And then we have the protocol analyzer, which is like pretty much a end all be all, can test everything for these devices, but it's really expensive and it's hard to justify using it when you can just use one of the previously described equipment.
Determine what devices they are. So you connect a breaker box to one end and see if it's pin 1 or pin 2, pin 3. If it's pin 2 is on, then the device is probably DTE. If pin 3 is on, that's probably DCE. You can also check by inspecting what type of connector it is. So males, like we said before, are usually DTEs, and the females are usually DCEs, but they're not always. There are also two approaches when troubleshooting the system. The first approach is if the system was never turned on before and never used. The system could have the following three possible problems. mechanical, setup, or noise. If the system was already working, then the only problem it is a mechanical problem. In all systems, it is best to check the mechanical parts first. Verify that the power to the equipment, verify that connectors aren't loose, and verify that the wires are correctly connected. You can also check that a part, board, or module is not visibly failed.
So here we have some more various mechanical problems that can come up when you are looking at these different systems. So first of all is during installation, you want to make sure you use short stranded wires to help prevent some of these problems. It also may be a problem with the speed and distance of your system. Like we said earlier, it's recommended you have a shorter than 50-foot and in between the range of 115 to 200 bits per second for the speed. You want to make sure you have a difference of at least 5 plus or minus 5 voltage between pin 1 and pin 2. If you're using a breakout box, or you can use a breakout box to test some problems by connecting it to pin 1 and 2 and ensuring that both the lights are on to see that both of those connections are good. You can also test the BUAD rates using the protocol analyzer that we talked about earlier across pins 1 and 2. That'll help you if the rates aren't similar, then you'll know that there's a problem there. You can also test the timing of it. So this is again using the protocol analyzer. If you get the communications error or failure message, then you'll know that the receiver is either not responding or it's getting an incorrect response.
So you can check the following conditions before trying to communicate anything. Is a software communication set up at both ends for either AN1, E71, or 701? Is the baud rate the same at both devices? And is the software set up the proper type of control? Most asynchronous communication used 8 data bits, no parity, and one stop bit setup. Most common setup for industrial equipment is 7 data bits, even paired with one stop bit. The most common baud rate used in asynchronous communications is 9600.
So here we have some different noise problems that you may encounter. First of all is ground-induced noise, which is obviously caused by different voltage levels on the ground pin itself. You can fix this by simply changing the location of the ground. You might also have some induced noise on the TX or RX line. This is also caused by excessive voltage across either one of those lines. You can try fixing that by replacing the connector you use for those. You may also get induced noise on the control lines themselves. It's kind of the same as the issue with the TX or RX lines, but it's a lot more difficult to find where the issue is. So you can try doing this by using an oscilloscope to measure the voltage on the line to find which line is faulty, and then you can try replacing that link.
So some of these examples are that since it's an open standard, many of the companies that refer to the protocol while making their own products, so many companies are able to use this open protocol. One of the main companies that uses the EIA-232 standard is IBM.
And that's all for the EIA 232 standard interface.